from the depths of the universe. It all began with one moment. Discover the secrets of the universe, with the series Exploring the Universe. Look up at the night sky. It's a tapestry of stars, planets, and galaxies. Each point of light holds mysteries, each galaxy teems with possibilities, but have you ever wondered where it all came from? How did this vast and intricate universe come into being? The answer, my friends, lies in an event of unimaginable scale and energy: the Big Bang. This wasn't just any explosion, it was the birth of everything we know and love. It was the moment when space, time, and all the matter in the universe burst forth from a single point. Imagine a universe smaller than an atom. It's almost impossible to comprehend, yet, from this infinitesimally small point, our universe sprang into existence. The Big Bang Theory, supported by decades of scientific observation and research, is our best explanation for this incredible cosmic origin story. So, buckle up as we journey back in time. We're going to explore the mind-boggling science behind the Big Bang. We'll uncover the secrets of the early universe and discover how everything we see around us came to be. Get ready for an awe-inspiring adventure through the cosmos. First things first, let's get one thing straight. The Big Bang wasn't your typical explosion. When we hear explosion, we think of something happening in a pre-existing space. We picture fireworks scattering debris outward, or a bomb detonating in a specific location. But the Big Bang was different. It wasn't matter exploding into space, it was space itself expanding, stretching and growing rapidly in every direction at once. Imagine a tiny balloon suddenly inflating to an enormous size. That's a closer analogy to the Big Bang. Now you might be wondering what existed before the Big Bang. That's a question that has puzzled scientists and philosophers for ages. The truth is, we don't have a definitive answer. The laws of physics as we know them break down at the singularity, that point of infinite density and temperature, at the very beginning. Think of it like asking, what's north of the North Pole? It's not that there's nothing there, it's that our current understanding of direction doesn't apply in the same way. Similarly, our current understanding of time and space might not apply to the universe before the Big Bang. The first few moments after the Big Bang were a whirlwind of activity. We're talking about timescales so small they make a blink of an eye seem like an eternity. In these early fractions of a second, the universe was an incredibly hot, dense, and energetic soup of fundamental particles. Imagine a universe crammed into a space smaller than an atom. The temperature was a mind-boggling 10 to the power of 32 Kelvin, hotter than anything we can create in a lab. At these extreme energies, the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces were unified into a single force. As the universe expanded, it also cooled rapidly. This cooling allowed for the separation of the fundamental forces. Gravity, the weakest but most far-reaching force, was the first to become distinct. Then came the strong force, responsible for binding atomic nuclei. Within the first second, quarks, the building blocks of protons and neutrons, began to bind together. Electrons, those negatively charged particles that orbit an atom's nucleus, also emerged. However, the universe was still too hot and energetic for atoms to form. Instead, it was a seething plasma of charged particles. Now, let's fast forward a tiny bit, to about 10 to the negative 36 seconds after the Big Bang. At this point, the universe experienced a period of exponential expansion known as cosmic inflation. During inflation, the universe expanded faster than the speed of light. Before you say, but Einstein said nothing can travel faster than light. Remember, it wasn't matter moving through space, but space itself expanding. Imagine a tiny dot suddenly swelling to the size of a grapefruit in a fraction of a second. That's the kind of rapid expansion we're talking about. This inflationary period smoothed out the early universe, explaining why it looks remarkably uniform in all directions today. Cosmic inflation is a crucial part of the Big Bang Theory. It explains several observed features of our universe, such as its large-scale structure, and the uniformity of the cosmic microwave background radiation, which we'll discuss later. While the evidence for inflation is compelling, it's still an active area of research. Scientists are working to understand the exact mechanism that drove this rapid expansion and its implications for our understanding of the early universe. Section 5. From light to matter, the first elements emerge. As the universe expanded and cooled, energy began to condense into matter. This process, known as baryogenesis, is one of the universe's most fascinating chapters. Einstein's equation, E equals mc squared, tells us energy and matter are two sides of the same coin. In the early universe, energy could transform into matter and antimatter. For every particle of matter, there's an antiparticle with the same mass but opposite charge. When they meet, they annihilate each other in a burst of energy. A slight asymmetry allowed matter to dominate. As the universe cooled, quarks formed protons and neutrons. 3 minutes after the Big Bang, these particles fused, creating the first atomic nuclei. Section 6. Echoes of the Big Bang. Evidence in the afterglow. We've been on quite a journey through the early universe, but how do we know any of this actually happened? Well, the Big Bang Theory isn't just a cool story, it's supported by a wealth of scientific evidence. One of the most compelling pieces of evidence is the cosmic microwave background radiation, often called the afterglow of the Big Bang. About 380,000 years after the Big Bang, the universe had cooled enough for atoms to form. Before this, the universe was a hot, dense plasma that scattered light. But once atoms formed, the universe became transparent, allowing light to travel freely for the first time. This first light, which has been traveling through the universe ever since, is what we detect today as the cosmic microwave background radiation. It's a faint, uniform glow of microwave radiation that permeates all of space. Think of it like the heat you feel radiating from a campfire long after the flames have died down. The cosmic microwave background radiation is the heat signature of the Big Bang, and its discovery in 1964 revolutionized cosmology, providing strong support for the Big Bang Theory. Section 7. A Universe in Motion, Expansion and Beyond. The cosmic microwave background radiation isn't the only evidence that points to a Big Bang origin for our universe. Another crucial piece of the puzzle is the expansion of the universe itself. In the 1920s, astronomer Edwin Hubble made a groundbreaking discovery. Galaxies are moving away from us. Not only that, but the farther away a galaxy is, the faster it's receding. This observation, known as Hubble's law, implies that the universe is expanding, like dots on the surface of an inflating balloon moving apart from each other. But here's the thing. The expansion of the universe isn't just about galaxies moving through space. It's about space itself stretching and growing. It's like baking a loaf of raisin bread. As the dough rises, the raisins, representing galaxies, move farther apart from each other, even though they're not moving within the dough itself. The expansion of the universe is a direct consequence of the Big Bang. It's like the after effect of that initial burst of expansion, and it continues to this day. In fact, recent observations suggest that the expansion of the universe is accelerating, driven by a mysterious force we call dark energy. Section 8. Cosmic structures, stars, galaxies, and our place in the cosmos. Now let's fast forward billions of years. The early universe, once a hot, uniform soup, has cooled and evolved into the complex cosmos we observe today. But how did we get from that smooth, featureless early universe to the intricate tapestry of stars, galaxies, and galaxy clusters we see now? The answer lies in tiny density fluctuations present in the early universe. These fluctuations, amplified by gravity over billions of years, acted as seeds for the large-scale structure of the cosmos. Imagine a perfectly smooth lake. Now imagine dropping a few pebbles into the lake. The ripples created by those pebbles will eventually intersect and interact, creating a more complex pattern on the water's surface. Similarly, the tiny density fluctuations in the early universe, amplified by gravity, led to the formation of stars, galaxies, and galaxy clusters. Over billions of years, gravity drew matter together into denser and denser regions, eventually collapsing under their own weight to form stars. These stars, grouped together in vast collections, became the building blocks of galaxies, and galaxies themselves clustered together, forming the vast cosmic web we observe today. Our own Milky Way galaxy, home to billions of stars and countless planets, is just one small part of this grand cosmic structure. Section 9. The Unseen Universe. Dark matter, dark energy, and the mysteries that remain. As we've journeyed from the Big Bang to the present day, we've uncovered some of the universe's most closely guarded secrets. But the story of the universe is far from over. Some of the most exciting chapters are still being written. Observations suggest most of the matter in the universe isn't the kind we're familiar with. It's something else entirely, something we call dark matter. Dark matter doesn't interact with light, making it invisible to our telescopes. Yet, we know it exists because of its gravitational effects on visible matter. And then there's dark energy, that mysterious force accelerating the universe's expansion. We know even less about dark energy than we do about dark matter. It seems to be a property of space itself, pushing everything apart. These are just two of the many mysteries that continue to puzzle cosmologists. The study of the universe is a journey of endless discovery. The Big Bang Theory provided a framework for understanding the universe's origins, but it also opened up a Pandora's box of new questions that will keep scientists busy for generations to come. So the next time you look up at the night sky, remember that you're looking at the afterglow of creation, a universe still evolving and full of wonder. The Big Bang wasn't just the beginning of the universe, it was the beginning of our quest to understand it, a quest that continues to inspire awe and ignite our imaginations. The study of the universe is a journey of endless discovery. The Big Bang Theory provided a framework for understanding the universe's origins, but it also opened up a Pandora's box of new questions that will keep scientists busy for generations to come. So the next time you look up at the night sky, remember that you're looking at the afterglow of creation, a universe still evolving and full of wonder. The Big Bang wasn't just the beginning of the universe, it was the beginning of our quest to understand it, a quest that continues to inspire awe and ignite our imaginations.